Hi everyone, my name is Apostolos and I'm going to talk about our work on improving failing level classification with adversarial training. Deep learning has achieved impressive results in many state-of-the-art tasks, but for doing so it requires access to a lot of training data. In reality though, this is not always the case, and one can think of multiple examples where the access to the training data is quite limited. To alleviate this few data problem, transfer learning is commonly used. In transfer learning, one can train a neural network on a very large training dataset, which is the source domain, and then use this pre-trained network to fine-tune it on the target domain, where the data are scarce. And by fine-tuning, we mean that one can just update the parameters of some layers, like the last layer, the last 2 layers, 3 layers, or even the whole network. To give you a real-world example where the data are scarce, one can think of tasks that include human-to-robot collaborations, where we ask for the robot to infer the world from just a few observations. A particular use case could be the manipulation and handovers of different objects, and specifically containers or drinking cups and glasses. For succeeding in this task, one should be able to estimate the weight of the container. And by this, we mean you have to infer the dimensions, so the volume of the container, but also the amount of content within the container, which is the filling level. And actually the latter is the one that we really focus in this one. So estimating the filling level can be actually quite challenging. On top of the few data problem, one can think of constraints on the vision modality. For instance, one can have access just to RGB data. Also, many challenges appear in the differences in the shape, in the transparency of the container, but also to occlusions occurred by the hand. And in general, you can think of many more challenges like the material of the object, the type of content, and differences in the illumination in the background. A few works have tackled this problem, where usually they observe the action of pouring content in the container. So they have access to video sequences. And one can use RGB and depth data and be able to track the level of the content during the pouring. And on top of that, some works can also use thermal data in order to identify these pixels of heated liquid. The most challenging case in this problem is when one has access just to still RGB images. And this is challenging because on top of the few data problem, you don't have any other depth, temporal, or material information. The best solution so far in these problems is to use transfer learning, and specifically to use a classifier trained on ImageNet and then properly fine-tune it to your target task. However, even if transfer learning gives the best solution, the actual results are just a bit better than random chance. So the question here is why transfer learning doesn't give the desired outcome, and in fact, how can we improve it? And in this work, we show that if one first applies adversarial training on the source domain and then performs transfer learning, then that can improve transfer learning and achieve state-of-the-art results. To give first some preliminaries though, consider a classifier denoted as F that is able to classify this image X properly as a castle. Then one can take the exact same image and add some very small perturbation delta. And by small, we mean that the norm of the perturbation is below some threshold epsilon, which is usually small, and create an image, a perturbed image that looks identical to the original one. But if now you give this new perturbed image to the model will predict something entirely different. So this perturbed image we call adversarial example. And how can one avoid this problem? How can one create more robust networks? And the answer is adversarial training. The only thing you have to do if you want to become robust to such type of adversarial examples, you can train your network, but instead of using the natural examples, you just use the adversarial examples. But why do we care about adversarial training in the first place? Well, it has recently been shown that adversarial training improves transfer learning. In fact, if one applies adversarial training on the source domain and then fine-tune on the target domain, it is enough to achieve state-of-the-art results in many computer vision tasks. The question we have here, though, is, would this technique work for filling level estimation? And the answer is we don't know, because this is quite a novel task. And also we don't know how to, what parameters could actually lead to the best performance. And if we go one step further, we can ask ourselves, what will happen if we perform adversarial training on the target domain instead of doing it on the source domain? So to answer these questions, let's see what is the setup we should follow. First of all, we're going to use ResNet 18 as a network, but this holds for different other types of classifiers. And how you can train this ResNet 18, this classifier, you can go directly to your target domain and perform standard training or even adversarial training. On the other hand, you can perform transfer learning, where here the idea is that either you follow the standard transfer learning technique, or you also transfer and you do adversarial training on the target domain. And if you swap somehow the relationship, you can do adversarial training on the source domain and then either fine-tune or do adversarial fine-tuning on the target domain. So these are actually the 6 strategies we're going to use. And in terms of data, we generate a new dataset, which comes from image crops from the QMUL containers manipulation dataset. That is a dataset of large variabilities in terms of transparencies and shapes, etc. In total, we have 8 objects, which are 4 cups and 4 drinking glasses, that constitute around 10,000 RGB images. About the filling level, these containers can be empty, can be filled 50%, 90%, and we also have a class we call unknown for dealing with cases of opaque objects, like the red cup, where in some cases we cannot infer, even as humans, what is the filling level inside it. And finally, about the material we have inside the containers, this can be water, pasta, or rice. To further investigate if there are some biases in terms of the shape, so to understand the effect of the shape of the containers to the performance, we create 3 different configurations. In the first configuration, both in the train and the test set, we have containers of regular shape, but also containers that have some stem. And the most challenging case can be the champagne flute, where it has a stem, but also the shape above the stem is not very regular. It's quite similar to the stem. In the second configuration, we take every container that has a stem and we put it in the test set. In this way, we make sure that during training, we will never see a container with a stem. So we ask here how the classifier will perform when we show it during test time, some container with a stem. And finally, on the third configuration, we do the opposite, where every stem is placed on the training set. And now we want to see if the classifier can practically generalize the test set by just the few observations it has over the regular shapes. And now that we know the setup, let's see what are the results of these experiments. The first thing we analyze is the effect of the different layers we freeze during transfer learning. So we perform a sensitivity analysis and we measure the accuracy of the classifier on the test set when different layers are fixed or frozen during transfer learning. What we see here is that for all 3 configurations, the best performance can be achieved by fixing the first layer only. And then we see that if we fix more layers, then the performance drops. And this can be justified by the fact that if we freeze more layers, then we decrease the freedom of the classifier to learn features from the target task, since it uses mostly features from the source domain. The next thing we need to analyze is what should be the size of the perturbations when we perform adversarial training on the source domain. Recall that epsilon is the perturbation size. And we see here, after performing a sensitivity analysis, that the best value of epsilon depends on the dataset actually. And this somehow makes sense because every dataset configuration contains different features. So then your adversarial training should be properly tuned in terms of epsilon in order to have the desired effect on the actually learned features. And now let's see the overall performance of the task. So we see how the 6 training strategies we propose perform on each dataset configuration. And in particular, we check each container individually. As a general comment, we can say that adversarial training on the source domain, followed by fine-tuning, which is the green bar, on average performs best. In general, transfer learning helps, for instance, the yellow bar, and it avoids overfitting to the training set. But still, when you also combine with adversarial training on the source domain, you can achieve state-of-the-art performance. And as another general comment is that if we perform adversarial training on the target domain, either directly or either after fine-tuning in transfer learning, then this does not seem to help. But let's take a closer look. In the first configuration, we see that for the champagne flute, if we don't use transfer learning, then the classifier cannot cope with the shape above the stem. Nevertheless, If we use transfer learning and specifically combine with adversarial training, then we can almost double the performance. For the next two containers, the beer cup and the cocktail glass, every method performs almost similarly. And the reason behind that is that the shape of these containers somehow appears in the training set as well. Because for the beer cup, we have the small transparent cup in the training set, which is similar but a bit smaller. And for the cocktail glass, although it has a stem, then the shape above the stem is quite regular. So that's why almost every method performs the same. If we go to the second configuration, we see again the problem with the champagne flute. Recall though here that in the training set, we don't have any object that has a stem. So here, again, adversarial training on the source domain followed by fine tuning gives the best performance. And this is actually more striking if we go to the next objects, where we start seeing that where the shape above the stem is quite regular, but still many methods does not perform as well as the one that uses adversarial training and then fine tuning on the target domain. And finally, if we go to the last configuration, we have a quite surprising effect on the accuracy of the red cup. In fact, if you don't use transfer learning, the accuracy is almost 0%. We checked a bit the predictions of what's going on, and almost always these classifiers predicted that this cup is 90% full. One possible explanation is that the opaque red cup resembles a lot some transparent cup that is full with some opaque content, like rice or pasta. And as a result, transparent plus opaque gives you some opaque container. Nevertheless, if we apply transfer learning, we immediately improve the performance. And specifically, again, if we use adversarial training on the source domain, we achieve the best possible results. About the green glass, although most of the methods perform similarly, the accuracy is not that great. And perhaps this is due to the fact that the color and the reflection of the cup somehow affects the overall performance of the classifier. Still, again, if we combine transfer learning with adversarial training on the source domain, we achieve the best performance. And finally, for the beer cup, as explained in the first case, all of the training schemes perform in a similar way. And that's because in the training set, we still have the small transparent cup, which is very similar to the beer cup. To conclude, in this work, we tackle the problem of estimating the content level within a container, and we treat it as a classification task. We're using a new dataset that comes from the coarse-mal containers manipulation dataset and has a large variability in terms of shape, content, and transparencies. We investigate different training strategies and try to understand how the classifiers overfit to specific features of the data, such as the shape. And finally, we show that transfer learning helps, especially if you combine it with adversarial training in the source domain, because in this context, you can actually achieve state-of-the-art results and further improve transfer learning. Thank you for your attention, and I wish to see you at our poster.